Hi dear children, I invite you to another chapter, and the name of the chapter is atoms. The concept of atoms you started learning say around 6th or 7th class. If my information is correct, it is 7th class. And we know that, or we were known at that time that atom is the smallest constant of matter as proposed by John Dalton. He gave the name atoms from the Greek word atomos, that means something that is indivisible. Later, atoms were also divided after the discovery of electrons by Sir J.J. Thomson. There came the model called the plum pudding model proposed by J.J. Thomson. And according to the plum pudding model, what the model states is that, think like the plum, or think like a cake in which the seeds, or what I'm saying, the plum, the nuts that is plum inside the cake is considered to be the electrons, because then only non-particles were electrons only. Or just straight with a watermelon, we know that the seeds represent the electrons and the fleshy part represent the positive charge. Later, his research student Sir Ernest Rutherford proposed the Rutherford's atom model, or precisely saying Rutherford's planetary model or nuclear model, both we say planetary model or nuclear model. And according to the model, what was the significance of this model was that the model predicted the existence of the nucleus, it predicted the charge on the nucleus, it predicted the size of the nucleus. Everything was predicted according to that model. The model was proposed by Sir Ernest Rutherford. Later it was performed by Geiger and Marsden. And so we are going to start our session by studying the Rutherford's atom model. According to the Rutherford's atom model, alpha radiations from beryllium. So whose energy is 5.5 million electron volt or mega electron volt. It was made to strike on a thin gold foil of size about 0.21 micrometer. 0.21 micrometer. What is this size? It is much smaller than our plastic carry bags. You have to understand. The size of the gold foil is much smaller than the normal plastic carry bag size, around 30 microns. This is just 0.21 micron. So understand how sensible was this experiment. How much care was required to conduct this experiment. Everything is very important. So this is the thickness of the gold foil they use for the experiment. Now let us quickly consider their experimental arrangement before we come to the important observations of the model. So there is a source of alpha radiations. These are lead blocks. The purpose of the lead blocks is to absorb the radiation which are going beyond a certain limit. Now this arrangement will provide you a fine narrow beam. So as per the figure shows, it is some wide, but in reality the separation is very small, such that this will form like a collimator. The purpose of a collimator is to form a narrow beam. Now it is made to strike on a thin gold foil. Okay, let us use a different color for drawing the thin gold foil. This is the gold foil, right? Gold foil which is placed by means of a supporting stand. Then this incident alpha particles were what I'm saying, this will scatter, and it was detected by a circular detector. It was detected by a circular detector, circular screen. This is coated with zinc sulfide, and then we have got a microscope, so traveling microscope that will measure the number of alpha radiation. So this is how it represents. This micro detector, which is a microscope detector, nothing but a microscope. So this is the angle through which the incident alpha radiation is scattered. So let me tell you, this is the experimental setup. So lead blocks. The purpose of the lead blocks is to absorb those alpha radiations which is moving at an angle. So if you consider an alpha particle like this will be absorbed here, absorbed here, absorbed here, absorbed here. So what happens is that this lead blocks will allow it to move as a narrow beam, I have to say. Lead blocks will allow to move the alpha radiations at a narrow beam and made to strike on a thin gold foil. Okay, let us find out the observations of Giger and Marsden. So first observation, let me tell you about 0.14% of the incident alpha radiations deflected by more than 1 degree. About 0.14% of the incident alpha radiations got deflected by more than 1 degree. So you have to understand what is this 0.14%. 0.14% is 1 by 700 approximately. That is observation number 1. About 0.14% of the incident alpha radiations got deflected by more than 1 degree means on an average when 700 alpha radiations are incident, only one got deflected by more than 90 degree. Yes, this is point number 1. Point number 2, 1 in 8,000 deflected by more than 90 degree. 1 in 8,000 on an average, 1 in 8,000 deflected by more than 90 degree, and the third observation is 1 in 20,000 deflected by 180 degree. 1 in 8,000, that means when 8,000 alpha radiations are incident on the gold foil, one got deflected by more than 90 degree. When 20,000 alpha particles were striking on this thin gold foil, one got deflect, one retraced its path. That means one has gone that way, come back. That's it. One retraced its path. That's me. So these are the observations of the model. So then my question, let us come to the conclusions. Conclusion number 1. Why is these numbers very few? Conclusions. We are coming to the conclusions. Why these numbers are very few? That itself concluded that most of the space in an atom is empty. That is conclusion number 1. Most of the space in an atom is empty. That is conclusion number 1. Right? So these observations show that most of the space in an atom is empty. Nothing is there in the atom. Now the question, why alpha particles undergo deflection? Very simple. So there is a small region in an atom. There is a small region in an atom where entire mass and positive charge is concentrated. So when I say entire mass, I will use the word almost. Almost entire mass and positive charge is concentrated. Let me explain. Alpha particles have positive charge. So if alpha particles undergo deflection means, suppose if it is this is the incident ray and this undergoes a deflection means, so the charge here located is also positive charge. So that's the reason why deflecting likewise. Now white rebounds. Rebounds means alpha particles undergoes a collision with a heavy object. That's the reason. Just like a ball colliding with a wall. When a ball collides with a wall, the ball rebounds because the mass of the wall is much greater than that of the ball. Right? Or otherwise, when you play caroms, when the striker strikes a coin, the coin moves. But when the striker strikes the edge of the table, carom board table, the table is not moving because compared to the size of the striker, the size of the carom board is large. So when it makes a head-on collision, it rebounds. So when you strike normal to the edge, it rebounds only because the mass of the striker is negligibly small compared to the mass of the carom board. That's the reason, right? You might have observed that. So that's the reason. So that is why we say the atom has got the entire mass of the atom as well as, almost the entire mass and the entire positive charge is concentrated in a small region. And Sir Ernest Rutherford called that region of the atom by the name nucleus. So please understand, one of the important features of this atom model is it proved the existence of nucleus. Rutherford's atom model. So what is the significance of Rutherford's atom model? If I ask you, your answer should be the model predicted the existence of what is called a nucleus. Nucleus is that part of an atom where the entire mass and entire positive charge and almost the entire mass is concentrated. The model also predicted the size of the nucleus. The size of the nucleus predicted as 10 raised to minus 14 meter to 10 raised to minus 15 meter. This is the size of the nucleus predicted by the Rutherford's atom model. How? So I'm going to ask to say this is 10 raised to minus 4 to 10 raised to minus 5 times the size of an atom. Ten raised to minus 4 to 10 raised to minus 5 times the size of an atom is the size of the nucleus. Let me tell you. So you understand this clearly. This is an important point I'm coming to. The size of the nucleus. Now, how he was able to predict the size, upper limit of the size of the nucleus? He was able to predict it through two important aspects. The first one is called an impact parameter. Impact parameter. So what is impact parameter? Let us explain this. Okay, consider a situation. This is a nucleus. Now this is the initial velocity vector of the alpha particle. The initial velocity, V0 I am saying. Now this is the line passing through the center of the nucleus. Now it will undergo scattering, and this angle of scattering is a theta. Now this distance is B. Yes. Impact parameter is defined as perpendicular distance between line passing through the center of the nucleus of the nucleus and initial velocity vector of the alpha particle. Line passing through the center of the nucleus and initial velocity vector of the alpha particle, that distance. So if you look at this one, that distance is called impact parameter. Mathematically, impact parameter is given by the equation 1 by 4 pi epsilon 0 z is square cot theta by 2 divided by the initial kinetic energy in mega electron volt. 1 by 4 pi epsilon 0 z is square cot theta by 2 divided by initial kinetic energy in mega electron volt or million electron volt is the expression for impact parameter. Now some constants are involved here. Z, what is Z here? Z is the atomic number of target nuclei. Atomic number of target nuclei. Ek, initial kinetic energy. Initial kinetic energy of the alpha particle. Incident alpha particle. So Ek is the initial kinetic energy of the incident alpha particle, right? So let us come to that point. Ek is the initial kinetic energy of the incident alpha particle. Now from here one more shortcut we can derive it. So 1 by 4 pi epsilon 0 is a constant, charge of the electron is a constant, so this will be 1.5 into 10 to the power minus 15 Z cot theta by 2 divided by the kinetic energy of the incident alpha particle in million electron volt. Million electron volt. This is the expression for the impact parameter, let me tell you. The expression for impact parameter is this much. So this is very, very important in solving. The second point which was predicted the size of the nucleus was the distance of the closest approach. Distance of closest approach. So what I mean by distance of closest approach? Let me tell you. Consider an alpha particle. Okay, let us wipe the board again. Consider an alpha particle which is subjected for a head-on collision. What I understand that it can approach up to a certain distance before it retraces the path. Right? At this point, the velocity becomes zero, right? So we can see that initial kinetic energy at that point. So at the point P, the entire kinetic energy of the alpha particle will be converted to the electrostatic potential energy. Then I can say 1 by 4 pi epsilon 0. The charge of the nucleus is Z, charge of the alpha particle is 2e divided by R0. K, Q1, Q2 by R. That's the formula I use. From here I will get R0 is equal to 1 by 4 pi epsilon 0 2z square divided by R0. Sorry, Ek. Again I can make a shortcut from here. R0 is equal to 3 into 10 to the power of minus 15. Z divided by Ek in mega electron volt. What is Ek? The initial kinetic energy of the incident alpha particle. The initial kinetic energy of the incident alpha particle is Ek. So this shortcut will enable you to understand or solve problems easily. This is the expression for the distance of closest approach. We will consider an example from NCERT book, example 12.2, where it is given that the initial kinetic energy of the alpha particle is 7.7 mega electron volt and Z of the gold nucleus is 79. You are asked to find out the distance of closest approach. You are asked to find out the distance of the closest approach. What will be your answer? Okay, solve it. So we can easily solve this. R0 is equal to 3 into 10 to the power minus 15. Z is 79 This is 7.7, right? Mega electron volt. This is also in mega electron volt. So you can just substitute in the formula and get the answer. So your answer will be approximately, this can be cut to 10, approximately 30 into 10 to the power minus 15 meter. So that is about 30 Fermi. Answer is 30 Fermi. So simple is this calculation if you reduce to this formula, let me tell you. I hope this idea is clear to you. The next topic that we are going to discuss is regarding the energy levels in hydrogen atom according to the Rutherford's model. Yes, energy levels. Let me consider this. Positively charged nucleus and electrons are revolving around the nucleus. So let us say that at one instant its velocity is v and this distance is r. So electrons are negative charge. There is a force towards the center that is called a centripetal force. mv square by r is equal to k into the charge of the nucleus. I am considering for hydrogen atom, so Z is equal to 1. K square divided by r square, so 1 r will be gone. What is the expression for kinetic energy? Kinetic energy is equal to half mv square. Already we have mv square on top. This is k e square divided by 2r. Kinetic energy is k e square divided by 2r, that is kinetic energy, right? Equation number 1. Now potential energy, very simple, K into Q1 that is plus E, Q2 minus E divided by R, which is minus K E square by R. And I can say this is equal to minus 2 times kinetic energy, which is equation number 2, right? Now what is total energy? Total energy is the sum of kinetic energy and potential energy. That is equal to minus kinetic energy, you can easily say, because potential energy is 2 times kinetic energy. Now you have the important equation, the ratio of the kinetic energy to potential energy to total energy as you studied in gravitation. 1 is to minus 2 is to minus 1, right? So that is the reason why we say, that the Rutherford's atom model is also called the planetary model of atom. Rutherford's atom model is also called the planetary model of atom. So we will now discuss example number 12.3. And example number 12.3 states the binding energy of hydrogen atom is 13.6 electron volt. Binding energy. Binding energy means what? Sorry, the energy required to separate. Actually the question says the energy required to separate a hydrogen atom into electron and proton is 13.6 electron volt. That means how much energy I have to supply in order to separate hydrogen atom into electron and proton? Already the energy with which they are bound, right? So which means I can say energy total for hydrogen atom is minus 13.6 electron volt. I put this minus only because the force is attractive. That is equal to minus kinetic energy, right? Minus kinetic energy. So from here we can find out the velocity of hydrogen atom, right? So 13.6. 13.6 is equal to half into 13.6 electron volt is equal to half mv square, right? Now from here we can see that v square is equal to 2 into 13.6 into E by m, right? That's it. Or v is equal to 2 into 1.7 into 10 to the power 11 into 13.6. Right. So I can say v root of, right? or I will say this is root of 34 into 13.6 into 10 to the power 10. Root of 34 is approximately 6. Right? Root of 13.6, 11 square is 11.5 I can say. Sorry, not 11.5. Is about 3.6 into 10 to the power 5. Not 11 point, 13.6. 3.6. Root of this one is 3.6. So this is 21.6 into 10 to the power 5 meter per second, which is approximately 2.2 into 10 to the power 6 meter per second. That is the velocity of electron in the ground state of the hydrogen atom. Now the second thing we need to find out is the radius, right? Again I will say minus 13.6 is equal to minus Ke square. Okay, sorry. Minus 13.6 electron volt is equal to minus Ke square by 2r. This electron and one electron volt. So R is equal to 9 into 10 to the power 9 into 1.6 into 10 to the power minus 90 divided by 2 into 13.6. Yes, we can guess the answer. 0.8. This is 7.2 divided by 13.6 into 10 to the power minus 10 meter. So we can say around approximately 0.53 angstrom. That's the answer for the radius. So this is example number 12.3. This is the radius of electron in the first orbit of hydrogen atom. And that's all for today's class. In the next video, we will start Bohr atom model and its applications. Thank you and have a nice day.